I want to thank Sean for inviting me, and also it's really great to join some of my colleagues from the Stats Lab on this lovely busy day to the MRC Biostats unit. So I'm glad to present some recent work I've been doing with Rajan at the Stats Lab on harnessing expert randomness. Okay, so I focus on what is called a randomized procedure. What is a randomized procedure? Those are procedures where the output is a random function of the data. So basically, you have two pieces of information. One is the data, the other is a piece of extra randomness. You can imagine this by throwing a die, or more conveniently, by running your pseudo-random number generator. And these two pieces of information would pass through some algorithm that computes a score for you, such as a statistic. It usually further leads to a decision, for example, acceptance or rejection of a hypothesis. So you can imagine, even if you have the same data, had you have a different piece of extra randomness, you could as well get a different score and leads to a different decision. So these randomized procedures are quite prevalent nowadays, and a prominent example, as I guess you guys all heard of, is data splitting. So that is the practice simply to randomly divide your data points into several parts for different purposes. So imagine this is the collection of random data points. Now I randomly divide them into the blue and yellow sample, and such random division would afford independence between the two samples, and that is quite important. And we can use such independence to control overfitting and to prevent double dipping. So a point I will get back later. So these are other ways you can introduce extra randomness in your procedure, such as through sampling. So suppose these are your data points. I can sample according to some weight, usually for the purpose of approximating a different distribution other than the sampling distribution. And on that different distribution, I can compute some score. And another scenario is where you have missing data in your data set, and you can use some random imputation algorithm to fill out the missing points and then compute some score based on the complete cases. Okay, so through this talk, I will first try to illustrate that there are serious drawbacks associated with randomized procedures, and then present a general framework to resolve these drawbacks, and finally show you how to use my proposed procedure to harness extra randomness and enable applications. Okay, so if you allow me, I will first try to illustrate the dilemma of data splitting by introducing two fictional characters. So the first character is called Bill, who's an epidemiologist. So Bill is interested in this problem of understanding the infection of Helicobacter pylori on blood pressure. And for this purpose, he wants to estimate this causal effect using some observation data. He collected some covariates, such as gender, age, what you eat, that suffices to control the confounding between the two. And then he wants to use now this fairly standard, doubly robust or double machine learning estimator for the causal effect. So the double robust estimation would usually also require estimating nuisance function. In this case, the two familiar pieces, eta 1 and eta 2. Eta 1 is the probability of infection given the covariates, and eta 2 is so-called the outcome regression model, namely the conditional mean of blood pressure given the infection status and the covariates. Okay, so to run these double or targeted machine learning approaches, the benefit is that they would allow you to use really flexible machine learning tools to estimate those nuisance parameters. So that avoid the risk of using some parametric model that could be severely misspecified. So a gradient of those double or targeted machine learning approach is the practice of data splitting or cross-fitting. And these are introduced to control the overfitting bias of those nuisance functions. So here's how that works. Imagine these are data that Bill collected. Now randomly divide them into the blue and the yellow. On the yellow, I run my machine learning algorithm to fit these two nuisance functions. And then I plug in those fitted nuisance functions into another sample to evaluate an estimator for this causal effect. I call that tau1 hat. Then to cross-fit, I basically swap the rows of the two samples by first fitting the nuisance on the blue, and then evaluate the statistic from the yellow. That gives me another estimator. I call that tau2 hat. Now, the double machine learning estimator is simply the arithmetic mean of the tau1 hat and tau2 hat. Okay. Now imagine Bill has collected the data, installed the software, and he now wants to try out the method. Okay, I want to hide this bar a little bit. Okay. So because there is going to be randomness every time Bill encounters anything random, he's very cautious. He sets the seed to his favorite number, 42 in this case. Now he calls the software. Okay.
Click on the screen again.
This again, all right. Okay, I hit the enter, and this gives me my estimate. So on some unit, the infection status would increase blood pressure, and the causal effect is positive. And Bill is really excited because if you look at the p-value, it's rather significant, 0.004. Okay, this seems a good result. However, Bill just curious, what if I used not 42, but at the next integer? Well, the tau is still a positive estimate, but all of a sudden, the p-value is not that encouraging. It's no longer significant. What about 44? Well, positive effect, not significant.
Is this a real example, or is this?
Well, real example with some storyline. Okay, but this is totally imaginable. I mean, this is a case you can totally encounter if you do this sample splitting stuff. Okay, but suppose you're a Bill, now what would you do? Well, here's what Bill thinks. Bill thinks, well, wait a minute, why should I bother running 43 and 44? Well, I didn't do any cheating. I started with 42. I've been always using 42 all my life. So it did give me a significant result. I should just stay with this and report it, shouldn't I? Well, as you may disagree, but actually Bill is theoretically justified, because if it is a randomized procedure, I only take the first realization, it has marginal statistical guarantee. So Bill is all right. So Bill decides to report the first result in his paper, tau hat, 1 p-value 0.004, 95% confidence interval, but with a fine line. He says to replicate his analysis, you better also use 42. But as you can imagine, this could caught by a very observant reviewer who says, well, to replicate, why must I use your special number 42? Why can't I use my own number? And this can be exacerbated by more pungent criticism that how do I know you did not fish for that special number 42? You go through the numbers, you find 42 is very significant. Then you suggested I should also use 42. Okay, so this seems to be an issue, but I'll come back to Bill in a moment, but let's look another fictional character, Laura, who's a cancer biologist. And at the same time, she also has a master's degree in statistics. Okay, so Laura's research area is kidney tumor, kidney cancer. So for kidney cancer, there are 4 or 5 already well-established subtypes of kidney tumor. And Laura has run into such a subtype of kidney tumor. She collected some sample, and these are the cells she collected in a test tube. Now, Laura is really interested, could there be any new subtype of undiscovered kidney cancer cells? And she really wants to answer this using data, using technology. This is the single-cell mRNA sequencing data that she obtained from her test tube sample. So on the rows, you have cells, hundreds of thousands of cells. On the columns, you could have 100,000 genes, and the numbers are gene expression levels. And she wants to really use this data to answer this question. Okay, so normally for single-cell or mRNA sequencing data, people proceed with some unsupervised learning methods such as clustering, trajectory analysis, but these are not really formal ways to test this hypothesis. So Laura wants to formalize this question as really a statistical test. So the null hypothesis would be, all the cells in her sample, they come from a distribution that is unimodal. There is only one mode. With the alternative being the cells, they come from a mixture of different modes. So this is a multivariate distribution with 2 or more modes. Although I'm only drawing here in 2 dimensions, but you should imagine this is data from 100,000 dimensions because you have 100,000 genes. Okay, so how do we test this? Well, apparently you can't test it with a clustering algorithm because it's just unsupervised learning. And even if data come from one single mode, the clustering algorithm would also tend to split it into spurious clusters. Okay, so how do we test this hypothesis? Well, here is a concrete proposal. Okay, let's just do this thought experiment. Suppose all the cells, they do come from one single mode. It's a multivariate unimodal distribution. Then you should hold that no matter in what direction I look at the data, I should always see a univariate unimodal projection. In contrast, if the data, they do come from a cluster, a mixture of clusters, then there must exist a certain direction. If I look at the direction, that should give me a bivariate, a univariate bimodal or multimodal distribution. Okay, so if I just look at testing unimodality versus bi or multimodality on the single rail line, then this is pretty much a solved problem. In fact, this is heavily studied in the 80s, and there is this famous test called the DIP test, developed by the Hartigans, that exactly for testing this problem on the rail line, univariate. Okay, but how do I find the direction? Well, here is the proposal. We can use a clustering algorithm to find the direction. I can cluster the data and look at the direction connecting the centroids of the clusters. But there is still a caveat that Laura is aware of, that you can't use the same data twice. You can't use the same data to both find the direction and test a hypothesis along the direction. That would be double dipping. That does not guarantee the p-value type 1 error. So simple strategy is to do data splitting. Okay, so this leads to what I call a hunt and test procedure for hypothesis testing. So how does that work? Suppose this is Laura's sample. Now we randomly divide it into the blue and the yellow sample. On the blue sample, I run my favorite clustering algorithm that gives me 2 clusters. I connect the centroids that define the direction. Then I apply my direction to the other part of the data. Then I look at the projection of the other part of the data along that direction and applied Hartigan's DIP test to that projection. This is a univariate test for univariate unimodality. And this defines the p-value of my whole procedure. Is that clear? Good. Okay, now Laura is eager to try this out. Now she coded this up on her laptop, and she wants to try this for 10 times because there's going to be randomness. All right, so these are the p-values that Laura got. Okay, so 10 p-values, one of them is very significant, the other 9 are not so much. Okay, how would you interpret this result? So would you say that there is sufficient evidence to declare a new subtype of kidney cancer? How many would you say yes? Yes, for yes? Anybody yes? So I would assume all of you would go with Laura, who pessimistically declares that there is no evidence for a new type. However, because I'm building this up, so I can tell you, in fact, Laura made a mistake because in her data, there is actually a new subtype of kidney cancer cells. So what's going on? Well, because this dimension is really, really high, so the clustering algorithm will really struggle to find the right cluster. For example, if I run it, then we'll cluster in this way, so the direction is wrong.
Can I ask before you continue?
Yes.
If there were 3 clusters there instead of 2 clusters, how would you get the direction?
Well, I mean, presumably, you can still do the same trick. I think there always exists a direction. So you could try to do the same way as I did.
Would they use both directions or
could do that.
all the directions?
You could do that, yeah. Yeah, I'll come back to this. Okay, so I think, so to understand this, basically the failure comes from the failure of the clustering algorithm because dimension is really high. So only 1 out of 10 times you will find the right direction that gives you a significant finding. And the other times you won't find the wrong direction that won't give you a significant result. Okay, so this illustrates another problem with data splitting that cost Laura a missed opportunity in scientific discovery. Okay, so up to this stage, I believe I have convinced you that there are at least 2 problems with randomized procedure or data splitting. On the left, we have Bill, who suffered from this replicability issue. The replicability is basically this extra randomness that you have left conditioned on the data. On the right, we have Laura. There's another issue that the randomized procedures typically also suffer from low power. So for the rest of the talk, I will try to propose something that addresses these 2 issues. And the idea on the high level is very simple. that presumably I can keep the same data and run my randomized procedure multiple times. And the question is, how do we properly aggregate the results from multiple realizations? Okay. All right, so let me set up the scene. Suppose I have data x1 through xn ID from underlying distribution P. I want to test the hypothesis whether P is under the null edge node versus under the alternative edge. So this is what I call the single split statistic. That is a function, Tn is a function of the data x1 through xn, and also omega. Omega is exactly this extra randomness I've been talking about. So omega is used to generate randomness for data splitting or for sampling, etc. So omega is generated independently of the data. Okay, so this defines a randomized procedure. So I'm going to make one single assumption, that is, this single split statistic is constructed such that under the null, it can unconditionally, asymptotically converges to a no null distribution, such as the uniform if the statistic is actually a p-value, or the normal, standard normal, if the statistic is actually like a z-score. Okay, I use the word here unconditionally. That means the randomness is taken over both omega and the data. So when I say conditionally, that means only condition on the data, the randomness is with omega. But for here, this assumption is posed unconditionally. Okay, so the randomized procedure is basically to take one single realization of this the single split statistic and compare it with the alpha quantile of this asymptotic null distribution. And depending on the side of the test, you want to reject it when it's smaller than or greater than the alpha quantile of the null. And obviously, we have seen that this suffers from high conditional variability and low power. Okay, so how do we fix this issue? So this is the natural proposal. So suppose I fix the data by generate L, big L, you imagine this is like 20 or 100 or something, independent copies of omega, and that gives rises to Tn1 through Tnl. I call them the multiple split exchangeable statistics. So why I call them exchangeable statistics? Because condition on the data, the omegas are all ID. So marginally over the randomness of the data as well, they are by construction exchangeable. So they are unconditionally exchangeable. So now I have this L-dimensional statistic vector. I want to aggregate them into a single number that I use for decision. So the single number is constructed through the aggregation function S. So I suppose you give me an S function that is aggregating this L-dimensional vector to a single number, and the S should be symmetric and Lipschitz. These are reasonable assumptions. And the examples would be the average of the statistics or the minimum statistics. For example, if your statistics are actual p-values, it may make more sense to take the minimum of the p-values. If the statistics is like a z-score where the signal is in the mean, then you probably want to take the average. Okay? So now I want to do my decision making based on this aggregated Sn. The only problem is what threshold, what critical value should I compare it to? Okay, but suppose I have found a good way of figuring out the critical value, then supposedly this provides a satisfactory solution to the two problems. Because I take a large L, then it should have reduced conditional variability. At larger L it is, then the less conditional variability remains. Then also presumably by using all the splits, I probably have more power against the alternative than using only one split. Okay, so the main challenge, I think, is quite obvious. How do we determine the critical value to compare with the aggregated test statistic? Okay, so let me ask you, so in the ideal case, what I should pick here as the critical value? Well, this is a test, so I should look at the null distribution of this aggregated statistic and take its quantile, and that should serve as a critical value. Okay, so if I look at the null distribution of the S, that obviously depends on the null distribution of the statistic vector, Tn1 through Tnl. Well, this can be further decomposed into two parts, the marginal null distribution and the dependency, or the copula. The marginal, by our assumption, well, this converges to a standard normal or uniform under the null, so this is fine. So the problem is with the copula. What is a copula? It is the statistical vector after I apply coordinate-wise the distribution function to each coordinate. Now, this marginally uniform statistical vector's distribution is called the copula. So actually, we don't know anything about the copula, except that it should be symmetric because it's exchangeable. But other than exchangeability, there's nothing we can safely say about the copula. Other than that, at the best, we can assume under the null, this copula would converges to some, tight copula, but we don't know the distribution of this copula. Okay, so this unknown copula basically is the main issue, and this is well aware in the literature. And in the existing literature, there are actually two types of approaches that depending on how they address this unknown dependency or copula issue. So the first type of approach is just assume you have some parametric copula and fit your data and then proceed with a fitted copula. For example, you can use a Gaussian copula, but it's fairly easy to construct examples where the copula is some monster. It's not any standard textbook distribution. It's some very bizarre copula. And this is an example that I don't want to go to details, but basically it's quite commonplace that the copula is not any standard textbook parametric copula. So if you apply this copula fitting strategy, then your model could be misspecified, and at the end of the day, you don't have type 1 error control. So there is another stratum of the literature that basically says, I don't know the copula, and I don't have anything concrete to say about the copula, so I'm going to guard against the worst case copula. So there is a large body of literature on such type of results that deliver type 1 error guarantee that may be conservative, but it is guarding against arbitrary dependency. And for example, there is this very cute rule that you have a bunch of p-values and you don't know the dependency, but you can take the average p-value and then multiply by 2. It can be shown that it's still a valid p-value. So there's such a conservative procedure. And there are also some new developments by Vladimir Vok and Rodowan on e-values and some generalized means. And also there are proposals more recently by DiCiccio et al. On quantile concentration inequalities, and also some work by Nikolai Mensholzen. But all of those, as you can imagine, they assume they're working under the worst case, but typically our data is not coming from the worst case. So the result is that typically when you apply these to data, they are very, very conservative. And at the end of the day, you don't have much power. Okay, so I'm going to introduce my approach here. Okay, as we already seen, the problem seems to be this unknown copula that prevents us to determine the proper critical value used for the aggregated test. Okay, so the simple proposal here that I want to estimate this unknown copula non-parametrically, and in particular, I want to use subsampling to estimate this copula non-parametrically. So suppose I have estimated copula, and then by our assumption, I know the marginal null distribution. So then I can combine them and call the resulting statistical vector T tilde 1 through T tilde L, and then apply my aggregation function that's called S tilde here. I query the S tilde's alpha quantile that serves as my critical value to compare with the aggregated statistic. Okay. But for some of you very observant here, well, I could be operating either under the null or under the alternative. How do I know estimating copula under either case? Well, under the alternative is a good choice. So I'll get to this. Okay, but before that, let me just illustrate the algorithm in picture. Okay, suppose these are my ID data point. I'm going to divide this into big B subsamples. You can imagine big B is a Monte Carlo sample size, like 500 or 1,000. And every subsample, I require the size of subsample to be roughly n divided by log n. So say n is 1,000, it's like 1,000 divided by 7. Okay, so those big B subsamples, they are allowed to be overlapped. Okay, suppose this is the first subsample, then I evaluate the exchangeable statistic vector using the subsample that gives me first the row of this realization. Then I go to the second subsample, I get another row of realization. I go to all the big B subsamples that gives me this subsample matrix, B rows, L columns. Yeah. Okay. So the rank transform is this step. So in I replace every entry of this matrix by its rank within the matrix. Now it's a matrix of ranks. Now I normalize the ranks by the total. So it's normalized to a number between 0 and 1. I claim at this stage, I have effectively non-parametrically estimated the copula. And then, as I said, I need to combine the estimated copula with the known marginal. For that purpose, I simply apply the known marginal's inverse CDF function to every entry of this matrix. Now I have got the T tilde statistics. So I apply my aggregation function row-wise. I get the realizations under subsampling of this aggregated statistic. I query its alpha quantile. That defines the critical value for my aggregated test. Any question here?
Are you going to explain any more of the details in the middle there?
In the middle.
So you replace each entry by its rank, and then you normalize the ranks, and then and that gives you a copula estimate.
Yes.
I didn't understand why that gives you a copula estimate.
Okay. So think about what is copula. Copula is a distribution after you apply the marginal CDF function coordinate-wise. Right?
Coordinate-wise.
Yes. So this is the statistic. So if I apply the CDF function to this column, that column, all the columns, I have basically turned this into a copula. Okay, let me go back to the definition of a copula.
I think I know what the definition of a copula is, but I still didn't follow. Maybe because it was just a bit too fast for me.
Okay, so this is the copula, right?
Yeah.
All right.
When you said it's an estimated copula, what do you mean? Like it's a matrix. So what do you mean by
the distribution? Okay, so the distribution of this guy, or the empirical distribution of this guy, is the distribution of the copula. Is the estimated distribution of the copula.
But just look at it
Row-wise,
by row, every row. So
Yes.
that's like an empirical
It's like a Monte Carlo
distribution
approximation.
of
Yeah.
the
Yes.
copula.
Yes. Is that clear? So
Each row is
each row is an L-dimensional vector.
yeah.
This L-dimensional vector, every coordinate is
On the previous slide.
here. Every coordinate is between 0 and 1.
Okay, one thing I don't understand is the 0.993.
Yes.
Is that saying that that particular value that you had up in that top left-hand corner is the 99.3 percentile?
Yes, exactly.
Of all of the entries in the table, or just the entries in the
All the
row,
entries in the
or
table.
all the entries in the table?
Yes, all the entries. Yes. That. So think about what is the definition of copula. Right? You have a vector. You apply the marginal CDF function to that vector. By exchangeability, every marginal is the same.
Ah, okay.
So I just need to count how many before me to estimate the CDF function.
Okay.
So I normalize it. That becomes the realization of the copula. If that's clear.
In this estimate, why do you use the entire matrix to get the?
That's just by exchangeability. Just by exchangeability. So I could just use the first column for the first coordinate, second column for the second coordinate. But by exchangeability, every column, they have the same margin distribution. So why not just put them all together?
Is that important? Does that make a big difference?
It does not make too much of a difference, but this stabilizes things a bit. Yeah.
Okay, so each row of that matrix now is a realization
It's a realization.
from the copula.
Yes, exactly.
Okay, okay. And so you say you got a copula estimate.
Yes.
We got a sample from
Samples
the copula.
It's an empirical estimate of the copula. Yeah.
Okay, it's a bit like an empirical distribution function.
Yes, it's like an empirical distribution function. Exactly.
Right,
Yes.
okay.
Yeah. Imagine this as Monte Carlo estimate.
Yeah. Okay, right.
Yeah. So then the combination of copula of the no marginal, I think is fairly straightforward. Now I just want to change the margin to the null margin. So I apply the inverse CDF transform of this known null distribution to every entry. That brings back to the scale of the statistic under the null.
Okay.
Then I apply my aggregation that's supposed to mimic how the statistic behaves under the null. I queries alpha quantile, that's my critical value. Okay, all right, cool. Good. I see there's something on the chat though.
It's been there for a long
It's probably
time.
beginning.
I'll get back to that later, I think. All right, so, okay, so how does this behave? So suppose I want to understand how this behaves.
So you're first gonna investigate how it behaves when the null is true,
Yes.
and then you're gonna do it when it's false.
Yeah, yes, you have, yes.
Okay.
Yeah, yeah, exactly. So how this behaves under the null, because I want to understand whether this has type 1 error control in the first place. Okay, so suppose I have L equal to 2, and the marginal distribution, null distribution is uniform. So basically, one pair of exchangeable p-values. Okay. Suppose now in this subsampling matrix, I have only 2 columns and b rows. Suppose I plot them on the unit square. So this is just like this is the empirical distribution of the copula, because now the margin distribution is uniform, so it's empirical distribution of the copula. So this is sampling under the null. So as I would expect, the null distribution is still uniform. And the aggregation function is chosen to be the average. So that is basic to project the points onto this diagonal line. I collect the projection. That is the histogram of my aggregated statistic. And here in solid curve, it is the null distribution of the aggregated statistic. And you see the subsampling is matching this up pretty well. And this is what I'm showing here is the subsampling matrix even before the rank transform. Okay, so what is the rank transform doing? If I apply the rank transform, then this is what I show on the right. You can see the rank transform barely changes the position of the points. So basically, after rank transform, the aggregated statistics subsampling histogram is still a good approximation of the null distribution function of the aggregated statistic. Okay, so this is as we desire. And this basically a proofing picture that shows that our method has type 1 error control. Basically, our test is asymptotic level alpha. And under further condition, it is also uniformly asymptotic level alpha, uniformly over the null. Okay, what is more interesting? Yes.
But that was all assuming that the F0 distribution, that was a uniform. So that's okay if your test statistic is a p-value, right? But not if it's
well, in this picture, I assume it's uniform, but in our theory in the paper, it could be uniform or a standard normal.
Okay.
Yeah, so either a z-score or a p-value. But suppose you have suppose you have chi-square here. You can always do a CDF transform to change the margin. So I think, this is not really losing any generality. Okay. Now, what is more interesting, I think, is the local alternatives behavior. So here, the data is coming from local alternative, and based on the data, I'm constructing this subsampling matrix, 2 columns, and I'm plotting here, and this is before the rank transform. Because the data is under the alternative, I expect the margin distribution is shifted towards 0 as what you expect from a p-value. And this aggregated statistics subsampling distribution now seems very different from the distribution of the statistic under the null. But this is where the magic of the rank transform happens, because lo and behold, if I apply the rank transform and replot it, can see now the margins becomes exactly uniform, but more striking phenomenon is here. If you look at the histogram or aggregated statistic after the rank transform, then unlikely this is still approximating the null distribution of the aggregated statistic, even though we're operating under the alternative. Okay, so basically, the reason is that when you move from the null to a local alternative, the margins seems to typically changes faster than the copula. So the copula, in other words, typically is locally stable. So that is, and this is a property you can show, for example, under local asymptotic normality. And using this result, basically by the rank transform, we can recover what the statistic behavior under the null, although we're operating under the alternative. And this is exactly what we want. Okay, so this is a formalization. So suppose the copula, so let me fix a null distribution function, null sampling distribution P naught. If in the neighborhood of P naught, the copula of the statistic vector converge in a locally uniform fashion, then along P naught's local alternative, then the power of our test is asymptotically no difference from the power of an oracle test. The oracle test simply has access to the aggregated statistics null distribution and uses alpha quantile as a critical value. So this is in other words, this is the consistency of the power result that says our test behaves on the zeroth order no different from an oracle test. Okay, so I guess you might wonder why I don't use Bootstrap. I instead use subsampling. Basically, for Bootstrap, that would require extra conditions about regularity, and I don't assume that. With subsampling, basically, I can get away with irregularity. Okay. So, as of late, we have some more finer analysis of the power behavior that I don't think I have time to go into, but basically, we can show that our test is much, much more powerful than the subsampling without the rank transform. And this power gap is increasing as with the effect size. So basically, if you're under a larger effect size alternative, then our test should be much, much powerful than subsampling test without the rank transform. Okay, so for the rest of the time, I think I just illustrate with applications. Yes.
What was the ordinary subsamplings? That way you just
don't do the rank transform. You just take the picture on the left.
Okay.
Yeah. Okay. So the Hampton test, okay, this is a fairly general strategy for testing what I call the conjunction hypothesis, the null hypothesis and intersection of a simpler hypothesis indexed by little d. So basically, you want to do data splitting, split the data, use one half to find the direction d, and use the other half to test the direction along the found d. In Laura's example, this is where I split the data, use clustering to find the direction, and use the other part to test univariate unimodality along the direction. Okay, let's see if we can help Laura. So here is a simulation. The sampling distribution is chosen to be two mixture of a high-dimensional uniform distribution over a high-dimensional ball or high-dimensional distribution of multivariate T, that the modes are separated at tau away from each other. When tau is 0, this is under the null, it's multivariate unimodal. When tau is positive, it's multimodal. So this is the single split statistics procedures power. And this is where I apply my method by aggregation 50 realizations using the average as the aggregation function. And you can see, especially on the top row, are a fairly evident power increase. And also the type 1 error is controlled when you look at the tau at 0. And this is the behavior when using different aggregation function, in this case, the minimum. And you could see the minimum seems to be working better, getting a bigger gain in the power for multivariate T. And we also have a version of our implementation that automatically adapts to the better or the best of a collection of aggregation functions. So basically, you can supply a few aggregation functions, and this adaptive procedure will automatically adapt to the power of the best aggregation function in your list. Okay. So this is just to highlight one of those conservative aggregation rules, and you can see the conservative aggregation rules is very conservative. It barely has any power for the multivariate T case. Okay, so this is a real data study. Okay, I just want to show you, this is a real data. And I have 111 kidney cancer cases, and these are already labeled. There are 3 subtypes, 37CC, 31P, and 43CH. So here, what I'm showing you is to the p-value, if I repeatedly run the single split low-risk procedure to every pure subtypes and every mixture of the 2 subtypes and a mixture of all the 3 subtypes. And you can see, I mean, at least for these 4, the p-values has quite a bit of randomness. That's where you see the p-value has this range. But if I apply my aggregation method, you can see a very clear-cut derandomized p-value, where for every pure subtype, the p-value is big, and for any mixture, the p-value is 0. Okay, so this hopefully illustrates Laura's application. Okay, I just want to mention there are many problems in the literature that can be aided by this framework. Now let's move to Bill's case. So if we recall, Bill has this problem of the p-value critically depends on the random seed. And actually, for double machine learning, if you look at the standard software package implementing the inference for double machine learning, there is another problem. Basically, standard error tends to be too small because these standard inference would ignore the finite sample correlation between the 2 splits, between the tau1 hat and tau2 hat. So I don't think I have time to go to the details, but basically, we can repurpose our procedure to deliver a better inference for double machine learning estimators using the rank transform. So here is just to illustrate with a simulation mimicking Bill's application. So N is the sample size and L is the number of splits, either 2-fold crossfit or 5-fold crossfit. And the nominal coverage should be 95. And the bottom row is the actual coverage of standard inference of double machine learning package. These tends to be undercovered. And with my method, bracketed coverage seems much closer to the 95 coverage. So this is another application that can aid the inference, very popular double machine learning crossfit estimation. Okay. Okay. So I don't know. Should I wrap up now?
Unless anybody says otherwise, I would say yes, wrap up.
Okay. Right. Yeah. I guess I just want to say for 30 seconds that there is another.
Don't worry. Yeah, 30 seconds, 2 minutes. Yeah.
Okay. There is yet another application I think would be interesting to show you, which is very different and seemingly unrelated. That is the analysis of a 2-stage randomized trial. Okay, so this comes up in the design of trials and also comes up in observational studies, like observation study for the HIV. Okay, so what is the scientific question here? Suppose here I have a 2-stage sequentially randomized trial. A1 is the first treatment that is randomly assigned. After A1, I observe the first outcome called L. Then the second treatment becomes assigned and is assigned conditionally based on A1 and L. This is conditionally randomized, A2. After A2, I observe the final outcome Y. And this represents the latent confounder that I don't observe, such as the health status that confounds L and Y. So the scientific question here is, suppose I have the data from such a study. I want to see if the first treatment has any direct effect at all on the final outcome. So why this is a problem? Because you could imagine if A1 is a drug that has some side effect, and A2 is only assigned, conditioned on your outcome, to aid the side effect, then it could be possible that fairly possible that all the effects from A1 to Y is all mediated by A2. So the drug is useless then. Okay, so why? So then in that case, you can just only give the second drug instead of the first drug. Okay, so this is a real scientific question. So how do we test this hypothesis? My hypothesis is that the first treatment has no direct effect for every person in the population on the final outcome. So this is the sharp null hypothesis. So although this seems very natural scientifically, but statistically it's a very bizarre hypothesis, because this hypothesis, surprisingly, is neither independence nor conditional independence. It is not any of these familiar hypotheses posed on the observed data. It's something else. So what is that something else? Okay, to understand what do I mean by this no direct effect constraint or no arrow from A1 to Y, so we have to look at a different trial, an idealized trial that we didn't run, which is the trial where A2, instead of being conditional randomized, is completely randomized. Its randomization does not depend on A1 or L. Then this no direct effect directly translates into independence between the first treatment and the final outcome. But you may say, we didn't run this trial, but you can basically retarget your current trial to this idealized trial through IPW weighting by this particular weight. Okay, so basically the null hypothesis of no direct effect can be formulated on a different distribution Q as an independence, where Q is related to P by a density ratio. And this motivates a randomized procedure. So basically, I can use sampling to retarget P to Q using this, according to this density ratio. For example, using a rejection sample, I can run a rejection sampler that selects a subsample that represent this idealized, completely randomized trial I didn't run. And on that trial, I can use any off-the-shelf testing procedure for testing independence. And that becomes a test for my no direct effect hypothesis. But this is obviously a randomized procedure. And now I can use my developed framework to aggregate multiple rounds of this hypothesis, of this procedure. This is only with one sample, single split. This is after aggregation, and you can see the error is controlled and the power is much higher. And surprisingly, I think for this case, we found that even with the same statistic, this seems to be more powerful than the standard in the literature, which is the IPW reweighting normal test. Okay, so I'm going to wrap up now. So I think on a high level, I think the philosophy of this talk is that the randomness is the livelihood of our statistician or biostatisticians, which can be quite useful. So a theme in this talk is that we can introduce this extra randomness, either by splitting or sampling, that usually can enable you to retarget an existing test to a new problem. But the downside is that it introduces extra randomness that causes replicability issue and lowers the power. So our procedure basically acts like this meta algorithm that can properly aggregate multiple realizations that delivers lower variability that also improves the power. Okay, with that, I would like to thank you very much.
Right, well, thank you. That was terrific. Do we have any questions?
Can I ask about Laura's example again?
Yes.
How is the uncertainty in determining the number of clusters taken account of in all this?
Okay, so the sole purpose of the clustering algorithm is to find a good direction. So in a way, the uncertainty in the number of clusters doesn't matter. I could use clustering to find a good direction, but I think you can devise other reasonable ways to find the direction. As long as there is some positive probability that you can find the right direction, then I can basically aggregate among
But
very many.
Were you fixing the number of clusters to 2, for example?
Yes.
Or were you estimating the number of clusters? That's what I'm trying to
But
understand.
if you know the alternative has 2 clusters,
Yeah, well,
if you know it, you'd better run a 2 means, right? 2 means clustering. But if you don't know the underlying clusters, say the alternative could be 2, 3, 4.
yes.
I would say,
So if you got 5 clusters, would you look at all the different directions and how does that come into your algorithm or the file?
that doesn't
matter.
that in a way, however you do it, you should have the valid error control under the null. It might be that maybe you do it more cleverly, that could give you a better power.
It's just that in each of your replicates, you might get different number of clusters.
That's fine.
Right?
That's
It doesn't
fine.
matter.
It doesn't matter. You just find some proper way of finding the direction. The only purpose of doing clustering is to find a direction. Yes.
Paul.
Sorry, I mean, I have a related question, I think. Sorry, really nice talk, by the way, before I ask my question. And so I'm again going to focus on that particular example, which I realise is, focusing too much perhaps on that example. So my question is, in that context, in terms of deciding whether or not there is an additional subtype, is data splitting actually something that people do in practice? Because I guess when I've seen people doing this, they would compare, a K component mixture to K plus 1 component mixture, and then do some kind of model selection between those 2 settings. So yeah, I'm just wondering.
I think the current status of the analysis is mostly exploratory.
Yeah.
And for very few limited statistical approaches, I think the statistical rigor in application is quite low, I think, actually.
So let me phrase my question another way then. Why should I prefer a data splitting approach to a model selection approach where I compare one component model, so just a single node clustering model, to a 2 component model? So
I guess the question is, so the purpose of this is to formulate it as a statistical test.
yeah, but you could formulate that as a statistical test as well. So for example, if you've got a 1 component mixture versus a 2 component mixture, then you could think about applying a likelihood ratio test to compare these 2 models, which doesn't work. I mean, so traditional likelihood ratio type null distributions are not valid in that setting. But this is something that someone like Jeff McLaughlin spent a lot of time thinking about in terms of building up an empirical null based on permutation or subsampling the data, which would allow you to give allow you to do a likelihood ratio test to compare those 2 models. So is there a reason why that's a bad idea? I guess that is my question. And so I mean, I can see that what you're talking about is far more general in this specific example. I just think is there a reason why the selection
So I think if the model selection can be formulated as a statistical test, there probably is also the viable approach. But my worry is, how does it handle really high dimensions? For example, you could easily have hundreds of thousands of dimensions.
Yeah.
How does the likelihood ratio?
It very poorly. So
So nice thing about this is you can basically, by this sample splitting and projection, you can bring this down to a 1-dimensional problem where you don't have cursor dimensionality. The rest is handled by this randomization.
that was part of your talk that I didn't quite follow, so I apologize but thank you.
Sorry, Oscar, go on.
Yeah, I was going to ask you if you have compared the performance of this method with Bootstrap, which is normal Bootstrap.
Yes.
All that you have showed can be done with Bootstrap easily too.
Okay, I do have examples that shows Bootstrap would fail to control type 1 error because
In pathological cases, Bootstrap fails. So, I mean,
not pathological.
the samples that you have shown can be solved.
I'm not entirely sure, actually, because Bootstrap's consistency relies on this pivotal regularity. And these things, once you're down the data splitting, usually that loses the
You
regularity.
don't do data splitting for Bootstrap. That's what I mean. Just for the example, those 2 examples can be done with Bootstrap.
Okay, so if you have regularity, then I agree, probably could do it with Bootstrap. But So basically, even if you do sample splitting, then you have multiple splits. And this multiple splits is not looking at one single statistic, is look at this vector of statistics. For bootstrap to be consistent, I believe you would need this vector of statistic to be regular. I think it's a fairly strong assumption, actually. Because if sample splitting in a way introduces some weird dependency that impairs this regularity.
I think we are talking about two different things, because you are talking about using bootstrap on data splitting, what you have described. But when my point is to solve these problems, you don't need to do data splitting. You can use this normal bootstrap.
I don't think so, because that would be double dipping. You would
not, because you are using bootstrap. You're using the sample that come with the bootstrap for the training, and the sample that are not part of the bootstrap sample as validation. That's the traditional way of doing bootstrap in testing and training.
Not sure I understand.
So imagine that you do a bootstrap sample.
Yeah.
And from a data set of 100, because you are using repetition, you are using the placement, you only get 80 samples of these 100. But some of them may come twice. Are you following? No?
Yeah.
Okay, so those 80 you use for developing your model. And the 20 that were not part of the bootstrap sample, those have not been used by training. You can validate your model or do whatever you want with the samples that are not part of the bootstrap sample. That's a traditional way of doing bootstrap.
Maybe we can talk offline, I'm not sure.
I'll just ask for questions. I'll have a look. I'll bring it up now. Okay, so we have a question online, but if anybody has any questions online, please, well, type something in the chat and I'll ask you to unmute. Maybe Nick, are you able to unmute and ask a question in person, as it were?
Yes, can you hear me?
Yes, we can.
Excellent. So really, this is a distraction, and I wrote the comment too early. So if I have to expand on it, this is a tirade against hypothesis testing. That is the weakness in the entire analysis. That the researcher or the analyst has to come up with a categorical statement: 0 or not 0. My view on it is that I would never bet on a 0, because I studied mathematics and I learned that 0 is just but one of uncountably many numbers, and uncountably many of them are extremely close to 0.
But this is a general question about hypothesis testing, isn't it?
Yeah, about now hypothesis testing.
Right. So you can answer if you want to.
Well, I would say if you don't like hypothesis test, you might still want to use confidence set or confidence intervals. And this does have some other applications in that aspect. Yeah, I don't wish to comment more generally on the usefulness of hypothesis test. But I would just want to say this is a fairly general approach, and the purpose of this is how do you properly derandomize and also deliver proper statistical inference.
Okay, do we have any more questions? I'll take one more online if there is another one online, and then Pantelis, if there are any more online. Okay, no. So Pantelis, please.
Thank you very much. A great talk. So I have one question, one clarification. When you were showing the results, you said that your method asymptotically has some properties. By asymptotically, is that the size of the original data set?
Yes, size original data set.
And in between, like how the sampling is done is not.
The sampling is done because in a way that the subsample size depends on the original data size. It scales like n divided by log n. But if you just fix this rate, then all the results will hold asymptotically.
The question related to that, I can imagine a question where you said about this copula that
Yes.
is the dependence between the different samples. Like if you increase some sampling ratio, you're probably increasing the dependence in this copula, right? And the overlap between some samples could be increased. And so that, will that increase the dependence?
No, so that dependency actually is not. I think the dependency I've been talking is the dependency come from two different splits. That is a dependency after you marginalize over your observed data. So it's a different notion. The overlapness in the subsampling does not by itself lend to dependence.
Okay, let's see. I've got a question, but I won't ask it. I think we'll stop there. Thank you very much indeed.